Alright, we're in the 5th video in chapter 7. We're talking about the quantitative composition of compounds. So using numbers, how we describe, using measurements and numbers, what the composition of a compound is. The main way we describe the composition of a compound from chemist to chemist is by giving a chemist a formula. If you have carbon dioxide, you're going to write down CO2. If you have glucose, you're going to write down in your biology classes C6H12O6, right? So formulas, the quantity of each atom that's present in a molecule or each ion that's present in an ionic compound gives us the formula of the compound. And that's the easiest way to quantify the number of each reagent. So let's back up real quick. And before we start talking about formulas, let's remind ourselves there's actually two different types of formulas. The first type is an empirical formula. An empirical formula. Empirical means purest or simplest. A molecular formula is the second type. A molecular formula. Alright, so let's discuss those. If you have a molecular formula of a substance, the molecular formula tells you the actual number of atoms of each element in that compound. So the actual number. For example, if you have glucose's molecular formula is C6H12O6. Glucose, I'm going to write MF for molecular formula, contains 6 carbons, 12 hydrogens, and 6 oxygens in one molecule of glucose. The molecular formula is different than an empirical or the purest or simplest formula. An empirical formula is the lowest whole number ratio of the atoms in the compound. So for example, in the molecular formula, the ratio we have of carbon to hydrogen and oxygen is 6 to 12 to 6. I think you can see that this ratio is not the simplest ratio we could have. All of the numbers are divided by 6, divisible by 6. The simplest ratio of atoms would be 1 to 2 to 1. If you divided by 6, you'd get 1. 12 divided by 6 is 2, and 6 divided by 6 is 1. So we take the molecular formula, and the simplest ratio becomes the empirical formula. Okay, so the empirical formula for glucose would be CH2O. Alright. Now, as it turns out, the molecular formula is related to the empirical formula because the molecular formula is always a whole number multiple of an empirical formula. Here I have this equation. It says the molecular formula of any compound or any formula is always equal to the empirical formula times some number n, where n is an integer. Whole number integer, 1, 2, 3, and so on and so forth. So let's do an example with glucose. We said the molecular formula of glucose was C6H12O6. We said the empirical formula of glucose, the simplest whole number ratio of atoms, is CH2O. How many times is the empirical formula repeated into the molecular formula? Or how many times do you go from the simplest to the actual ratio? 6 times. When we multiply the empirical ratio, or the empirical formula, by 6, we end up getting the molecular formula out. So the integer, or the whole number here, multiple is 6. Can you have a whole number multiple be 1? Meaning that the molecular formula is equal to the empirical formula. Can that ever happen? Where n equals 1? Sure it can. Let's look at the ionic compound, sodium chloride. Sodium chloride's formula, actual number of atoms, is NaCl. There's 1 ion of sodium for every 1 ion of chlorine. Okay? So this is a 1-to-1 ratio. That's the actual ratio of atoms or ions in the molecule, or I should say ion in a compound. The empirical formula is also the simplest. The simplest formula you can have is 1-to-1, right? Ratio of atoms. So if n equals 1, we see here that for sodium chloride, the empirical formula is the same thing as the molecular formula. Now, actually, this is going to be true for all ionic compounds. Remember, ionic compounds contain a metal and a nonmetal, or more well said, as a cation and an anion. Ionic compounds are physically not linked together by covalent bonds, but they're held together by strong forces of attraction, coulombic forces of attraction. So usually you're looking at ionic lattices. So you always describe the empirical formula, or the simplest whole number ratio, for an ionic compound. So that will usually be the case. Now let's look at what happens. I'm going to blow this up a little bit. The next question is it possible for different molecules to have the same empirical formula? The answer is going to be yes. It is possible for several different molecules to have the same empirical formula. Let's look at how this happens. An example is an empirical formula of CH. Let's just do a hydrocarbon. 1 carbon for every 1 hydrogen. If the empirical formula is CH, you have a 1-1 ratio of carbon to hydrogen atoms. If you look at the percent composition of carbon to hydrogen, if you have 1 of each, carbon weighs 12.01, hydrogen weighs 1.01, the total weight of your compound, if it was just 1 carbon and 1 hydrogen, is 13.01 grams. If you find the percent carbon in the empirical formula CH, it's going to be, 0.02, sorry, it's going to be 12.01 grams divided by 13.02 grams. Multiply that times 100. For the empirical formula CH, the percent carbon is going to be, 92.3% for that empirical formula, carbon. The percent hydrogen is the rest, equaling to 100, so 7.7. So the empirical formula CH, the percent composition by mass of carbon to hydrogen will be 92 to roughly 8, so 92.3 to 7.7. Let's take a molecule that has that empirical formula. One of the simplest molecules with that molecular formula is C2H2, ethylene. Here's what ethylene looks like if you wanted to look at its Lewis structure. This is the molecule of ethylene, C2H2. It contains 2 CH units. So the empirical formula here for C2H2 is CH. But that empirical formula is repeated twice in the molecule to give us the molecular formula. Now, what impact does that have on the characterization of this compound? Well, remember how we said the weight of the entire compound, if your compound was CH for the empirical formula, was 13.02? That's the empirical molar mass. Well, if you have C2H2, you've multiplied that empirical formula by 2, you have twice the mass because you have twice the number of atoms. So your total mass would be 26.04. Would you have twice as much carbon percent in your sample? Let's look at the percent composition. It's very interesting. Do you notice something about the percent composition of CH versus C2H2? The percent carbon and the percent hydrogen are the same, and it's because the ratio of the masses is the same. Instead of 1 carbon to 1 hydrogen, you have 2 carbons to 2 hydrogens, but that's still a 1-to-1 ratio. Because the percent composition of compounds is a ratio of the grams of one element to the grams of the whole compound, if that ratio stays the same, 1-to-1, the empirical formula is the same, they will have the same percent composition. Let's compare it to another molecule with the same empirical formula. So the compound is benzene. Benzene is C6H6. I'll draw benzene for you. Not the conventional way an organic chemist would draw benzene, but I'll draw benzene to show you all the atoms. So here's a Lewis structure for benzene. Benzene's molecular formula, the actual number of atoms in the compound, is C6H6. What is the empirical formula of C6H6? Well, instead of a 6-to-6 ratio, 6 carbons, 6 hydrogens, isn't that the same thing as a 1-to-1 ratio? It is. So the empirical formula for benzene, C6H6, is actually CH. But how many times is CH repeated in the molecule? 1, 2, 3, 4, 5, 6. There are 6 CHs inside of C6H6. I think you got that number probably without even seeing the molecule, but sometimes I think it's fun to see the molecules. I'm an organic chemist. All right, so there's benzene. The empirical formula is repeated 6 times in benzene. So, a 6-to-6 ratio, a 1-to-1 ratio. All right, let's see what implication this has on the molar mass. We said the empirical formula CH had a molar mass of 13.02 grams per mole, empirically. 13 times 6 is going to be 78.12. That's the molar mass of benzene. So we said the mass gets bigger. Does the percent carbon get larger? You see that it's going to be the same once again. The percent carbon in benzene is still 92.3 and the percent hydrogen is 7.7, just like the empirical formula, just like acetylene. As it turns out, compounds that have the same simplest ratio or the same empirical formula will always have the same percent composition. So the interesting thing is you cannot uniquely identify a compound by its percent composition alone. You can come up with the empirical formula from the percent composition. If you want to come up and identify a compound or its molecular formula, the actual number of atoms, you need a second piece of information. You need to know the total mass of the compound, known as its molar mass. Okay? So in order to come up with the molecular formula of a compound, you need probably an empirical formula or data to come up with an empirical formula, but ultimately you're going to also need the mass of the compound. So let's go ahead and talk about now how we're going to calculate an empirical formula. One of the things you're going to have to be able to do in this class is calculate an empirical formula from given data. It turns out that given empirical formulas can be calculated if you're given a percent composition of the compound. Or if you're giving the grams of each element in the compound, you can come up with percent composition. So if you're given the percent composition in a compound, you don't know the total mass of the compound. You just know the percents of each part. We're going to assume that, the percents always equal 100%. To calculate the empirical formula, the first step is you're always going to assume if you're given a percent composition that you have 100 grams of the compound. What is this going to do? If you assume that you have 100 grams of compound, you can immediately convert your percents, you can immediately convert your percents of each element into grams of element. So let's say you're given a composition and you have 64.2% copper. You can immediately, if you assume you have 100 grams, convert that to 2 grams of copper. Alright, so whatever the percent is, take away the percents and get grams. How does this work? Okay, let's say you have $100 instead of 100 grams. If I told you 64% of your paycheck went to taxes, if your paycheck was $100, if 64% of it went to taxes, how many dollars of it went to taxes? 64, alright? Because the percent is per 100. If you assume you have 100, you can convert automatically to the grams. Alright, so what happens after you get your grams of your element? After you calculate the grams of element, the second thing you're going to do is you're going to convert the grams of each element to moles. How do we convert grams of an element to moles? We have to use molar mass. This is what we talked about before. What we're going to do is we're going to take the mass percents we're given. We're going to convert them to masses. And if we then know the mass of each element type, we can convert those to moles. We're going to get a mole-to-mole kind of ratio, okay? The third thing we're going to do is to find the mole ratio of each element. This will be the ratio, a whole number ratio, all right? So I'll show you how to do that in a problem because I feel like it's easier to just show you than to explain it. And the fourth thing we're going to do is if we don't get a whole number with our ratio, we're going to multiply the ratio by some integer, some smallest whole number, in order to get the number of atoms to a whole number. We're basically going to be writing an empirical formula. Your empirical formula is never going to be x 2.4 y or something like that. You never see decimals. So we always want whole numbers in our molecular formulas or empirical formulas. So what we're going to do is we're going to calculate from the mass percents. We're going to convert to masses. So we're going to take the percents. If we assume 100 grams, we're going to convert those to grams. From grams, we're going to convert each of them to moles. And then from the moles of each element that we have, we're going to convert those to a simplest whole number ratio. Whoops. A ratio. Whole number. Alright, so let's do an example problem because it's the best way to learn this stuff. Okay, so let's read this problem. We're going to have to calculate empirical formula. It says calculate the empirical formula of a compound that has 63.19% manganese and 36.81% oxygen. Alright, so calculate empirical formula. An empirical formula is the simplest whole number ratio of elements in a compound. So the first thing I'm going to say is that there's two elements in this compound. Our molecular formula is going to be Mn something, oxygen something else. Whatever those whole numbers are, x and y, we don't know yet. So we have to figure out the simplest whole number ratio of atoms. If I have a mole of compound, how many moles of elements do I have? So whatever information I'm given, I'm going to convert it to a simplest mole ratio. So I've got to get it to moles. First thing we're going to do is assume we have 100 grams of the compound total. If I have 100 grams of the compound total, I've got my manganese, I've got my oxygen. The first thing I can do is take the percents and immediately convert them to grams. 63.19% mass of 100 grams is 63.19 grams of manganese and 36.81 grams of oxygen. Alright, now I've got the gram to gram ratio of manganese to oxygen, but that's not what I want. Empirical formula is the simplest mole to mole ratio of elements in a compound. So I'm going to convert each of these grams to moles using molar mass. I like to set up my conversions at the same time because I'm doing the same thing for each element. So for manganese, I'm going to convert grams of manganese to moles. Go on your periodic table. What is the molar mass of manganese? I see that it's 54.94. So 1 mole of manganese weighs 54.94 grams. So now I've got some math to do. Pick up your calculator. 63.19 divided by 54.94. I get 1.150 moles of manganese. Alright, let's do oxygen. This is the moles. It's not the whole number ratio yet. Now I've got my oxygen. I've got 36.81 grams of oxygen. I want to convert grams to moles. So on the periodic table, I see that there's 16 grams of oxygen for every 1 mole of oxygen. So 36.81 divided by 16, I calculate if I had 100 grams that I would have 2.301 moles of oxygen. Alright, so now I've got moles of manganese and moles of oxygen. That's considered my mole ratio. You're never going to write a formula at this step. You would never write 1.150 manganese, 2.301 moles of oxygen. That won't happen because you need the simplest whole number ratio. all empirical formulas, molecular formulas, are whole numbers, and we want the simplest ratio. Well, how do you come up with the simplest ratio? What you're going to do, and this is a math trick, is I think that some people actually see this. You can see that 1.15 is actually half of 2.30. So you could say this is a 1 to 2 ratio quickly in your head. But what if you can't do the math like that? The ratio of 1.105 to 2.301, if you divide both of those numbers, those moles, by the lowest number of moles, which is, in the whole mole ratio, it's 1.150. So we're going to divide both of these numbers, or moles, by the simplest, or the lowest number of moles. The answer that you're going to get is your simplest mole ratio. I don't know if it's going to be a whole number, but it will definitely be the simplest, because the simplest is always going to be 1. Notice if we divide 1.150 divided by 1.150, we're going to get 1 mole of manganese out of that. If we divide 2.3 divided by 1.15, we're going to get 2 moles of oxygen. Now, is that the simplest ratio? Mn1O2. By the way, we'd never write 1 there, right? A 1 to 2 ratio is the simplest ratio, and they're both whole numbers. So it turns out this is the simplest whole number ratio. This is the empirical formula, a 1 to 2 ratio of manganese to oxygen for manganese dioxide. All right, let's do it again. Let's find the empirical formula for this next compound. All right, it says calculate the empirical formula for a compound that is 72.2% magnesium and 27.8% nitrogen. All right, so we've got the percent composition of the elements in the compound, and we're asked to find the empirical formula. The key to solving these problems is to know the definition of what you're asked for. The empirical formula definition is the simplest whole number mole ratio of atoms. So basically, we need to take the numbers we're given, and whatever data we're given, we need to find out how to convert those to the simplest whole number mole ratio of atoms in an element, or in the compound. And then we'll come up with the empirical formula. All right, so let's write down what we're given first. We don't know the total mass of the compound. The first question you're going to ask is 72.2% magnesium by weight of what? Remember, assume you have 100 grams of material. So I'm going to just come to a clear screen rather than putting all that stuff in my way here. All right, so the first thing I'm going to write down is I'm given the percent composition. I'm given that I have magnesium and I've got nitrogen. So I'm going to list those first because those are going to be part of my overall molecular formula in the end, MgXNY. I'm going to figure out what X and Y are. I need to figure out the simplest whole number ratio of atoms in that compound. So I'm given the percent of each, 72.2% magnesium. If we assume 100 grams, I'm going to convert the 72.2% to grams of magnesium. Same thing for nitrogen. I'm given 27.8 grams of nitrogen, or percent, so I'm going to convert that to grams. Now I'm given the grams. We don't want a simplest gram to gram ratio. We want a simplest mole to mole ratio. So I'm going to convert those grams to moles. Notice I'm setting up my conversion factors using molar mass. Mass to moles use molar mass. So this is where you look on your periodic table. The molar mass for magnesium is, what is it? On your periodic table, 24.31. So 1 mole of magnesium weighs 24.31 grams. Notice I'm putting grams on top, grams on bottom. I'm converting grams of magnesium to moles of magnesium. When I calculate that, I get 2.970 moles of magnesium. All right. Now let's calculate the moles of nitrogen, because we want to go from grams to moles so we can get a mole to mole ratio. So look on the periodic table, what's the molar mass of nitrogen? There's 14.01 grams, notice grams on top, grams at bottom, for every 1 mole of nitrogen. All right, so 27.8 divided by 14.01, it's almost 2, 1.984 moles of nitrogen. Okay, now I've got moles of magnesium, moles of nitrogen. You're not going to stop here. You're not going to write 2.970, 1.984. You might see that this looks like 3 to 2. It does look like a 3 to 2 ratio. But what I'm going to suggest is you always follow the same method of solving. Remember, the next step here is we've got a mole to mole ratio, but it's not quite whole numbers. So you're going to take the numbers you've got and you're going to divide them by the smallest number. The smallest number in this mole sequence is 1.984. I'm going to move down here. Move down here. So for magnesium and nitrogen, for magnesium, when I divide 2.970 by 1.984, I get about 1.5 moles of magnesium. For nitrogen, when I divide the number by itself, I get 1 mole of nitrogen. Now, I will tell you, this is the simplest mole ratio. 1.5 magnesium to 1 mole of nitrogen. But is this the simplest whole number ratio? The answer is no. 1.5 to 1 is the simplest ratio, but it's not whole number. You can't have a half of a magnesium atom. That's scary. You can only have whole atoms. So what we're going to do is we're going to find the multiple. So if you ever get a fraction after you simplify, you're going to start multiplying by whole numbers. So let's say you get a 0.5. If you get a 0.5, let's just try saying, well, I know that if I multiply 0.5 times 2, you're going to do this to everything because you've got a mole ratio now. If I multiply this ratio 1.5 to 1 by 2, my ratio is going to be 3 to 2. Is that a whole number ratio? Yes, it is. And it turns out that's the simplest whole number ratio. And yes, it's the same as before. You could have gotten that in the beginning, but some people aren't sure if they should round or not. If it's so close to the whole number, as close as it is here, you actually are allowed to round. But some people, they like to simplify it first and then multiply up. Take the simplest ratio and then find the whole number. So we see we have 3 moles of magnesium for every 2 moles of nitrogen. So our molecular formula is Mg3N2. Not molecular, empirical. This is the simplest whole number mole ratio in the compound. Alright, so I think you're probably getting the hang of it. So here's another problem that I want you to try on your own. Okay, it's always best when you're studying or even in a lecture. You're watching these lectures and you're like, oh, this makes sense, I understand. Understanding is the first step to learning, not the last. The last step to learning, or the second step to learning, is trying it on your own. The last step of learning is being able to do it on your own without any help. If you can do that, then you're ready. You understand the concept fully. So here's another problem. It's another empirical formula problem. What is the empirical formula, the simplest mole-to-mole, whole number mole-to-mole ratio of atoms in a compound? What is the empirical formula of an alcohol? And here we're given this list of percent composition. Percent carbon, percent hydrogen, percent oxygen. So what's the empirical formula of this compound? I want you to try to solve this problem. So go ahead and press pause right now. Okay. Set your problem up. Convert percents to grams, grams to moles, moles to simplest mole ratio, and then make sure it's the whole number ratio. Give me that empirical formula. Because I'll give you the answer. Here's the answer. The answer is the empirical formula of the compound is C2H6O. A 2 to 6 to 1 ratio of carbon, hydrogen, oxygen. This is the simplest mole-to-mole whole number ratio. How did I get that answer? I'm going to show you my work so you can pause it if you didn't get that answer. Alright, so what I did first is I took all the percents of each element present in the compound. And I assumed I had 100 grams of compound. So I converted all the percents of each element to grams. Okay. After I have the grams of each element, I converted them using molar mass of the compound, or the elements known on the periodic table. I converted all the grams to moles. So here I have all the moles of each compound. So 4.314 carbon, 3.02 hydrogen, 2.17 moles of oxygen. This is the mole ratio if I had 100 grams. What would be the simplest mole ratio, though? What I did after that is I took my mole ratio, that wasn't simplest, nor was it whole number, and I said, what's the smallest moles in this group? It was 2.17. So I divided every mole by 2.17. When I did that, what I got was a simplest ratio. When you divide a mole ratio by the smallest number, you get the simplest ratio. And it turns out the ratio I got was almost close to the whole number, so pretty much they all just were whole numbers. I got a 2 to 6 to 1. Once you get the whole numbers, you stop. So this is my simplest whole number ratio. 2 moles of carbon, 6 moles of hydrogen, 1 mole of oxygen, the molecular formula C2H6O. Or the empirical, I keep saying molecular, the empirical formula C2H6O.